I'll present you our work on a simulator for DBT-based processors made in MLIR. Thank you. First, I present you what's a DBT-based processor and why we want to simulate it, and then how I made the simulator, and I finish with some feedbacks and conclusions on the project. So we search for an alternative to out-of-order processors. They may be the highest, they may have the highest performance from cores, but they have really poor energy efficiency because they have a lot of complex mechanisms to reschedule dynamically their instructions. An alternative is the VLIW core, the very long instruction word, which is very energy efficiency and may achieve out-of-order core performances, but they rely only on the compile time schedule, and they are not easily integratable in multi-core processor architecture. So we add a DBT layer to translate instructions and make a dynamic schedule in order to achieve the out-of-order performance level. What's a DBT? It's a dynamic binary translation. It may be seen as a software layer, as QEMU, for example, which increase the portability or is used to simulate architecture. Or it can be seen as a part of the processor design, like the Transmeta Crusoe processor, which use the TMS, the code morphing software, sort of DBT, to translate an ISA to the VLIW. It also hides the executed ISA from the application, from the user. That's a DBT-based processor. And here we want a DBT that generates efficient schedules dynamically without consuming too much time or energy to be a good alternative to out-of-order. We want to simulate the DBT because benchmark, because in order to fine-tune the decisions or the parameters of the DBT, like the threshold at which time it will translate a procedure or optimize it and take time to do that. But simulating it cycle accurate or changing the configuration at each run would be too costly. So we aimed on not simulating the VLIW because it's a really simple design. We just evaluate the schedules of the DBT and use MLIR for this. So we could handle large benchmarks and change the configuration of the DBT between each runs without having to pre-process all the benchmarks or reruns, re-synthesizing the DBT hardware parts or things like that. We choose MLIR because it's a complete compiler toolchain framework, and we wanted to have access to optimization passes, and also it gives us access to the JIT compiler, LLVM, and I already worked with LLVM, so it was a step in it. Now I describe how we implemented the project, the simulator. So let's get it technical. We first created a front end, so a dialect for simulated RISC-V, and a path to disassemble a RISC-V binary to the dialect we made, and a lowering path to have LLVM dialect, which is like basic dialect in MLA. And it's also the RV dialect in which we would have put DBT schedule passes, where we would have evaluated the schedules for the VLIW. For this step, in the end, we put it in the JIT compiler and execute it. For this step of disassembly and lowering of the RV dialect, we first had to reconstruct the control flow. So because as we take as an entry a binary file, but it only is a list of instructions. So we had to recreate functions on basic blocks, but in the end, the JIT can only be called on functions, and the MLIR doesn't allow us to branch from a basic block to a basic block in another function. So we made each basic block a function. So for an initial control flow, simple like this, a function with 3 basic blocks, a loop, the return in the end. We would have in the end 3 functions, a basic block in each of these, and they would tail call each other to emulate the initial control flow. And for example, the conditional branch would be translated in a conditional branch that would choose between 2 blocks that would be only a tail call to the correct function. The return instruction would be translated as it's an indirect jump instruction. It would be translated in a return that would return the target address of the indirect jump to the simulator, which would call the JIT on the target address.
Why? And this is great, but why do you want to JIT compile every basic block separately?
Because if we didn't find target in the first pass of reading the binary, we would have to cut a basic block. Hence, we would.
If you have not identified the proper boundaries.
Yes. We dynamical access to these blocks.
There is also the motivation for being able to schedule basic block instruction within basic block.
Yeah, but why at the granularity of individual basic blocks?
Because the DBT schedules instruction on the basic block. And so we wanted to play with that ultimately.
Here an example of code. So in the third block, we have binary instructions. We translate those in a function with blocks, and ultimately we translate it in the LLVM. Mimicking the previous control flow ratio. So let's then translate instruction themselves. As we translate binary instruction to simulated binary, we have to add accesses to the simulated component or emulated component. So for a simple instruction, we have to add the access to the register file. It enlarges the generated code and make it maybe difficult to have a simulation efficient, fast, at least. That's why we then in the LLVM dialect use optimization already implemented for the LLVM as it's a common optimization in compilers. And for example, if we had to translate two simple instructions that would make the same operation, it could enlighten the generated code. And then we use the JIT to execute the generated code and connect it with a simulation library to interface system calls and collect the metrics of the schedule the DBT made. That's our project. Now,
Is JIT already existed or did you work?
the MLIR JIT already existed. It is based on the LLVM JIT and sort of encapsulated. So we had to hack around to have access to some LLVM JIT features, but we didn't do more than tinkering. So the project is on by now, since a few months ago. But in the end, we could execute RISC-V binary files on any machine in theory that would can run MLIR. And we only tested it. The performance of the simulator didn't reach our expectation. It took 13 seconds to complete the small matrix multiplication. And we didn't implement the VLIW schedule we needed for the DBT simulation.
What does it mean, 13 seconds?
For the translation of from the translation of the binary to the execution and the print of the result.
Yeah, but
Why 4 by
But
4?
on my machine.
but maybe if
just,
you had like a 1000 by 1000, it would be 14 seconds.
maybe. Just the example that showed it worked, but
We move to something else in
so feedback on MLIR, my experience with MLIR. I think it has a great application field. We could do whatever we wanted to do on compiler flow. And also it has a JIT, maybe slow, it was but as Simon said, it's moving fast, so sometimes there are bugs, sometimes we had to hack around to have access to some features. And it requires a lot of time to even start a project, or I find the documentation very hermetic. So it was often very difficult to in the project. And ChatGPT will be of no use in this. Last time I tried, didn't understood what
You have to explain him. You have to explain him how to do MLIR first, and then he will be able to.
yes. So, easier web framework, he knows.
compared to, you had some experience with LLVM. So how would you compare the experience you had with LLVM versus MLIR?
For me, it was the same.
It was the same. You don't feel that there was much more documentation on LLVM? Much more specific? No.
I had the same problem in the two cases.
There was a project at some point about lifting, I forgot, I guess x86 to LLVM IR. Maybe more than one. I don't know if it's still alive. You didn't do that from National Taiwan University.
Someone is answer.
Maybe I tried at some point and I discussed it with the second layer. Maybe you got it from there.
No, I got it from conferences, like watching presentations, but it was, yeah, sometime back. Even at DAC, I think. Not sure whatever.
If we can just do a shameless plug, you said it's difficult to start a project. If you want to start a new project in MLIR, you can use the MLIR standalone template.
It's still difficult.
Is it up to date? It tries to be as up to date as possible. It should come from the again, and if there is an issue, you can always submit PR, or you can tell me it's not up to date and I update it.
And does your advisor agree?
You need a nerve on this.
Let's first thanks our speaker. And we already jumped into the question, but we can continue with a few more questions. There are some online or here. I'd be curious to have one. The original objective was to have dynamic binary translation, and you try to implement some of that in MLIR. Was it really a target to use the whole stack of MLIR to do your DBT? Because it seems to be, I've always heard, for example, the JIT from LLVM was saying, this is slow, do not use that for JIT. Because, yeah, and it's coming on with MLIR on top, which I guess doesn't help.
J'ai appris ça récemment, que le JIT de MLIR était déconseillé. Et
La motivation initiale
la motivation initiale, c'était de pouvoir d'avoir un simulateur de DBT qui nous donne des métriques sans exécuter le code généré.
un peu comme QEMU, tu voulais émuler en fait sans
Oui.
avoir à
Mais
exécuter.
en pouvant changer entre chaque exécution les directives qu'on donnait à la DBT pour essayer de trouver les bons paramètres.
Et aussi c'était pour essayer MLIR.
Il y avait beaucoup de ça. C'est pour ça qu'il y a du MLIR, on n'est pas parti sur QMU.
Juste, le JIT, c'est pas qu'il ne doit pas être utilisé, c'est qu'il ne faut pas l'utiliser dans un contexte où c'est time critical. Mais
Oui.
si tu veux faire juste quelque chose in process, tu n'as pas besoin de faire de file IO, etc. Bah, ça fait le job.
Oui, c'était un point de vue performance pure pour qui
Oui, non.
c'était déconseillé, sinon c'est sûr, ça a l'air solide. Je l'avais utilisé aussi dans ce cas-là. Et d'un point de vue, continuer question, d'un point de vue modélisation de performance, je sais que c'était sur QMU, en fait, c'est assez dur d'arriver à modéliser les performances d'un processeur. Est-ce que là, c'était quelque chose que vous arriviez à approcher ou que vous n'avez pas posé la question?
Bah, on partait du principe que, comme on ciblait un VLIW, ça va être très simple très stable, et très simple comme design. Donc, à partir du moment où on avait l'ordonnancement des instructions, on pouvait estimer les performances. Et donc, c'est pour ça qu'on ne s'occupait pas de simuler le VLIW.
Any other question in French or English? Thanks again.
Okay.